Okay, so we were looking at Lorentz transformations last time. Lorentz transformations. And we had already found that apart from an overall shift of the coordinates, which I was writing with plus a mu, okay, this is the most general transformation, and okay, that plus a mu is not counted as part of Lorentz transformations. Okay, so this is what how coordinates change under Lorentz transformations, and we saw that the constraint on lambda, okay, which was that if you have eta mu nu, then mu alpha lambda nu beta, this should give you back again eta alpha beta. Okay, so that's the constraint, and then we further saw that Lorentz transformation matrices lambda fall under 4 categories. Okay, one is proper orthochronous transformations, so determinant is +1, and lambda 0 0 is greater than 1. Okay, that is proper orthochronous. Let's denote it by L plus. So all the transformations which fall under this category, I will say that they belong to this part of the set. Okay, and then we also saw, or I think I asked you to do as an exercise, one of these, that any Lorentz transformation lambda can be written as a product of an orthochronous, proper orthochronous Lorentz transformations time parity operator, or times time reversal operator, or a combination of both, that you have both time reversal and parity. Okay, so these are 4 categories in which you can classify the matrices lambda, and the one here, this is the one which is continuously connected to the identity matrix. Okay, the no transformation at all. Identity corresponds to no transformation at all. Okay, so now what I want to do is I want to look at infinitesimal transformations near identity. So clearly I am talking about this part because identity element is only in here. These do not include identity elements because parity and time reversal are discrete transformations. So we are in this set, in this set, okay, and any transformation near identity I can write as follows. So of course in general I will write lambda mu nu x nu, and lambda mu nu, if there was no transformation at all, then you are sitting at the identity element, and that is just delta mu nu. But we are saying we are infinitesimally away from identity. So let's say omega mu nu, these are the parameters that parameterize how much further away you are from identity. So right now these are infinitesimal. Okay, what they are, we'll see in more detail how to interpret them, but right now we are just saying these are infinitesimal parameters which take us away from identity. Okay, so this is this. Now I can write the same thing. So here the first piece delta times x nu gives you again x mu. So the change in x is the x prime minus x, which is just this part. Okay, so your delta x prime mu is omega mu nu x nu. Okay. Now what I want to do is I want to bring the first index down so that both the indices on omega are lower indices and rewrite this. So, I can bring it down using a an eta, what do you call it? Yeah, metric tensor here. So, let me do that. Instead of putting mu, I will just write rho. So, del x prime rho is eta rho mu omega mu nu x nu. Let's see, nu is contracted, mu is contracted, only rho is free, and that is fine because only rho should be free as you have on the left hand side. Okay, we have already argued this in the last lecture that the omega with both the indices below, okay, is antisymmetric. It's a 4 cross 4 antisymmetric matrix. So, that is what I am going to utilize now. So, I write omega, okay, let's see what happened. Yeah, whatever I wrote was correct, but I just want to use sigma instead of nu. Does not matter, you can write nu. So, if I look at omega mu sigma, if you look at this 4 cross 4 matrix, okay, these are which is antisymmetric, it looks like this. So, because it is antisymmetric, all the diagonal entries are 0, and this one I call, this is omega 0 1, this is omega 0 2, and this one is omega 0 3, and due to antisymmetry it will be minus omega 0 1, just negative of this one should be 0, okay, and then here you should have minus omega 0 2, okay, this one let us call omega, not let us call, but it is omega 1 3, this entry would be 0, this one will be minus omega 1 2, okay, this one is omega 2 3, omega 0 3, this one, this is fourth entry. So, this one is 0, minus omega 0 3, minus omega 1 3, and minus omega 2 3 and 0. So, this is negative of this is negative of that, okay. So, that is fine. So, that is what it looks like. But you see, we have to know what is omega mu nu with mu up and mu down, not the omega with both the indices down. But that is easy, we can find that out. So, what we need is eta, this one, this thing, eta rho, let me write it like this, where is it, omega, this is omega rho sigma, which is same as eta rho mu omega mu sigma. This is what we are trying to find, okay, one index up, one index down, and that is easy to find because this is just, you take the eta matrix, take the omega matrix which is here with both down, okay, eta you know anyway, and then multiply them and look at what is the rho sigma element, okay, and that is what it will give you this one. So, that you can do easily, you can take the eta to be, you know what eta is. So, diagonal plus minus minus minus, okay, take that matrix, multiply with this one and look at read the omega sigma elements. That you can do, and you can, another way to do is this, you realize that you are raising the first index on omega, that is what you are doing here, right, by taking the eta, and when you raise the index with eta, it will not change the sign of the 0 when mu is 0, okay, but when mu is either 1, 2 or 3, then because when you are raising, it will change the sign because it is this matrix. Okay, so it will do nothing to the 0 index of mu, but it will change the sign of change the sign of the matrix elements if mu is either 1, 2 or 3. Okay, so that way it's again easy. So let me then write down what will be omega rho sigma. So omega rho sigma will be this. Okay, let's first write and then put the bracket. So this is fine. First index is 0, so I am looking at 0, 1 element. Nothing changes. Nothing changes. Nothing changes. Here, these will change the sign. Okay, see this is omega 1 0, which is same as minus omega 0 1, but the element is omega 1 0, right? This is the entry name is omega 1 0. So first index is 1, so it will change the sign. So I'll put minus omega. It will change the sign, so it will become omega 1 0, omega 2 0. Sorry, what am I doing? It will become omega 0 1, omega 0 2, omega 0 3. The signs have changed. Okay, and then of course this, the first index is 1, so nothing will happen. Sign will not change. Sorry, sign will change. 3. Okay, and this will become omega 1 2 0 minus omega 2 3 omega 1 3 omega 2 3 and 0. Okay, so this is what the matrix would be. Now remember that all these omegas which we have written, so there are 6 of them which are independent. The lower half is anyway completely determined by the upper half. These are independent of each other. So I can write the matrix omega rho, is it rho sigma? Am I doing everything okay? Or rho sigma, that is correct. Okay, so this can be written as the following. This is fairly trivial, but let me nevertheless write it explicitly and bore you guys a little. So I will write it as omega 0 1. Okay, what I am doing now is putting all the, I mean just I am writing it as sum of 6 matrices. That's all I want to do. Okay, so omega 0 1, omega 0 1, that you can factor out. It will leave behind a 1 here and a 1 here, and others. Anyway, I am going to split, so I'll put all others to be 0, and then add to it with omega 0 to omega 0 2 element, put everything else to be 0. So that's what I'm doing. So you can see that it will be the following: 0 1 0 0 1 0 0 0, and remaining are all zeros. Okay, so what you have here is everything 4 by 4. Okay, look at this block, it has all zeros here. Okay, then what do I have? Omega 0 2, and here you will have 0 0 1 0 0 0 0 0, and then 1 . Okay, while I am writing this, you can also write on your own without looking what I am doing, and then we can just match at the end. All these are 0 again. See, again this part is completely 0. all the things, all the entries in here are 0, okay, plus then you have omega 1 2 4 0 0 minus 1 0 0, this should be plus 1, okay. I hope you are also doing it with me, so that we never have to spend time on this again. Okay. And then you have all these as zeros. This one is minus 1. Third row is fully 0, and then this is 0. Something looks not good. Is that correct? Let's check. Omega 1 3. Let's go back. Omega 1 3, omega 1 3. So 1 here and 1 here. That's fine. Okay, that's correct. And the last one is omega 2 3. 0 0 0 0, and you have only entries in this one, okay. So if you have to take the rho sigma element, if you have to find the omega rho sigma, then I should be taking rho sigma element of these matrices, okay. That's what we should be doing, okay. So rho will be the first index, which will be the row index, and the sigma will be second index, which will be the column index. Okay, so now I can write it in short as half. Okay, there are 6 generators here. So these I will call generators. Okay, and the reason I call them generators is because you see these matrices are, see, the change in x is this much, and this change is being generated by these omega mu nu's, and the omega mu nu's apart from these parameters are controlled by these matrices. So these matrices are the ones which are generating the change in x, so we call them generators. Okay, so I will write this as, so omega 0 1, omega 0 2, omega 0 3, these are parameters, so I write them as omega mu nu, and these matrices, 6 of them I write as j mu nu. Okay, so these are, mu runs from 0 to 3, nu runs from 0 to 3, so it's 4 times 4 16, but then I remember that because this is antisymmetric, this will also be antisymmetric, actually, which, okay, I want to first put a tilde on this, so I don't want to call them as j's, but j tilde. Okay. Now, as I was saying that because omega is antisymmetric in mu nu, okay, j tilde has to be antisymmetric in mu nu. Okay, it will kill the symmetric part. If there was a symmetric part to j tilde, it will kill that part. So let's take the symmetric part, antisymmetric part. I mean, let's take j tilde to be antisymmetric, okay, and antisymmetric under mu nu interchange. Okay, it's antisymmetry under mu nu. But note that mu and nu, they do not label the entries of these matrices. See, mu nu labels which matrix you are talking about, whether you are talking about this matrix or that matrix or that matrix. The entries are labeled by the indices rho and sigma. Okay. So that has to be kept in mind. So let's see. So we have, for example, j tilde 1 2 is 0 0 minus 1 0 and 0 1 0 0 0 0 0 0. Okay, let's see where it is, omega 1 2, this one. Okay, this is the one I am talking about. Okay. Now I want to define j. So j mu nu, I will define it to be I times j tilde mu nu. Okay, and if I do so, then I get eta rho mu omega mu sigma. That is the quantity we have been looking for, considering since some time. So, this becomes minus I over 2 omega mu nu j mu nu and rho sigma. Okay, and the reason I have put a I here is that I want to make certain generators as Hermitian. So, let us see which ones. Okay, that is oh, I have already written something here. Let us see. Okay, let us skip this one. I will put a cross. So, let us go back. So, what will happen with because of this factor of I is, let us see where is j 01. This is j 01 or j tilde 01, j tilde 01. Okay. So, you have one here, one here. If you put a factor of I which is here, you will have an I here and I here. Okay. That is one thing. The other one, let us look at j 12. Where is 12 here? So, j tilde 12. If I multiply a factor of I to get j 12, it will be minus I here and plus I here. Now, this is that will be Hermitian, right? Because if you take a transpose and complex conjugation, that will give you again the same thing, because of the factors of I. Okay, so, what I have achieved by multiplying a factor of I in the definition of j is that j 0 I, let me write about j 0 I after I have written about j I j. These generators j I j, okay, these are Hermitian matrices. So, these generators become Hermitian and these one still remain anti-Hermitian. Okay, my interest was in making something Hermitian. If this is not becoming Hermitian j 0 I, that is fine, we cannot do anything, but the interest was in making this part Hermitian. But you do not have to do that, okay, but it is advantageous because we are going to do quantum mechanics eventually. Okay, so, let us just I think it will be a good idea to write them here for later convenience, later reference. So, j 12 becomes 0 0 0, what becomes 1 2 1 2 1 2 this. So, this will become minus I and this will become plus I, minus I 0. Okay, that is our generator j 12. And so, clearly this is Hermitian. If you take a transpose and complex conjugation, you get back the same thing. And let me also write down j 01. So, 0, this will give you what, j 01. So, j tilde 01 is both. Okay. So, you will get I 0 0, I 0 0 and everything else is 0. Okay, so good, and now we have shown that x prime rho is just del rho sigma minus I over 2 omega mu nu j mu nu. Okay. If I do not put a rho sigma here, that will be better. Let me write it again. Instead of writing delta, let me write identity minus I over 2 omega mu nu j mu nu. Okay. And then you have to take the rho sigma element of this and contract with x sigma. Okay. And this is what your lambda mu nu is, lambda rho sigma. That is the infinitesimal Lorentz transformation. Okay, that is good. Let's see what I want to say here. Okay, good. Now, note that we have already, I think this is the place where I want to, okay, maybe later. So, anyway, I was about to make a remark, but I will save it for later. So, this is what we have shown, and this is a result which we want to put in a box. Okay. Now, I have an exercise for you. Check that the following expression of J mu nu as a differential operator generates correct delta x, okay, delta x mu or whatever you want to write. So, check that if you take J mu nu, the generator, not in this matrix form, but in this form, I x rho del sigma minus x sigma del rho, okay. You take this one, okay, and plug in here. Then check that this is producing the correct transformation which you expect. So, that you should be able to verify. All you will have to remember in this entire derivation is that del rho and del rho are related by you have to raise the index by using eta mu nu, okay, that is what you have to do. And another thing is that del x mu over del x rho with rho up, that is what gives you, if okay, this is what you should use. And because here you have one index up, you have to contract with eta mu nu to raise the index. Okay. If you use this, you will be able to show that this indeed reproduces correct change in the coordinate x. Then you do another exercise, again not difficult. Calculate the following commutator. Calculate the commutator, commutator, okay, and the commutator is this. Take J mu nu and J rho sigma and find their commutator, and you will be able to show that this is equal to, let me first write before I give the expression, okay, maybe I should give the expression, I eta nu rho J mu sigma eta mu rho J nu sigma eta nu sigma J mu rho and then eta mu sigma J nu rho. Okay. This is what you have to show, and you start by doing the following. You write the expressions for J mu nu and J rho sigma. So, you will be basically looking at this object J mu del nu minus x nu del mu, and you put and you commute with find the commutator with this one x rho del sigma x sigma del rho. Okay, it's a fairly easy exercise to show that this result is true. Now, note that the whatever symmetry the left hand side has to be obeyed on the right hand side. So, left hand side is anti-symmetric under mu nu interchange. So, right hand side should also be anti-symmetric under mu nu interchange, right hand side is antisymmetric under rho sigma interchange, that should also be true on the right hand side. And also if you take this j mu nu and put here and take the j mu nu here and put there, you get a minus sign because you have a commutator, which means you also have antisymmetry under interchanging mu nu with rho sigma. Okay, so you should make these checks and show and check clearly that this is indeed the case on the right hand side. Okay, maybe I should write it down. Check that right hand side is antisymmetric under mu nu interchange, antisymmetric under rho sigma interchange, and also antisymmetric under mu nu getting interchange with rho sigma. Okay. Okay. Now, why I am interested in this commutator, and I will talk about this in a later video, but because this is such an important thing, I will put it in a box. Okay, that's going to be a very important object for us, and why I will tell you later. So, please do this exercise. You should do it both ways. You can use this to show it, which is going to be very easy, and okay, and you can also show using the explicit expressions of these matrices. Okay, both ways it will work. Okay, and that is also another exercise. Maybe I should write that also down. Verify the commutation relation. Using the matrix representation of J mu nu. Okay, please do these exercises. Okay. Now, we see that there are 6 independent generators. Okay. And we are talking about proper orthochronous transformations. You see, we are connected to identity, we are slightly away from identity. So, obviously, we are talking about proper orthochronous transformations. And if you put omega I j equal to 0, where I and j run from 1 to 3, then we are only talking about boosts. Okay. I think that is clear. Let us go back. So, what I am saying is, if I put omega 1 2, omega 1 3 and omega 2 3 to be 0, then you are left with only these 3 parameters. If we keep them to be non-zero, then you see this mixing is between the time component and the x component. This is in the time component and the y component, and this one is time component and the z component. Okay. So, this is clearly boosts, these are about boosts, and similarly, if you put omega 0 I to be 0, then we have only rotations. Okay. So, suppose you were looking at a Lorentz transformation such that these parameters omega 0 1, omega 0 2 and omega 0 3 were 0, then what you have here is only rotation. Okay. It is just mixing between. Okay, my battery is going low, just a second. Okay. So, okay, I think that is the reason why it was a bit dim. Okay. So, good, then now we understand which generators are generating rotations. So, these are J12, J23 and J12, J13 and J23, and the which ones are generating boost, they are J01, J02 and J03. Okay. So, what I will do is I will give names. So, as I said, J0I are generating the boost, so I call them, I give them a name Ki. Okay, that is the definition. And also JK, these ones are generating rotations. So, these ones I will define to be Ji, okay, where epsilon ijk takes value 1 when ijk are 1, 2 and 3, and if you, let me write down, epsilon 1, 2, 3 is 1, and every time you interchange any two indices, you pick up a minus sign. Okay. So, this is Ji. So, these are 3 generators for boost, 3 generators for rotations, and you have already seen that you have 3 for boost and 3 for rotations. Okay. So, for example, here this implies that J1 is J23, etc. Okay. Check how J1 and J with 1 index and J with 2 indices are related. So, this is one of them here. Now, yeah. So, let us go back and write down the following. Show that, shall I show this or shall, okay, maybe I will do it, even though it is fairly trivial and should be left as an exercise, but I will nevertheless do it. Let me do it on the next page. So, you had lambda rho sigma as identity minus I over 2 omega mu nu j mu nu rho sigma. Okay, that is what we had. So, let us look at this piece, half omega mu nu j mu nu. Let us look at this piece. This is what? Let us put half. So, mu, there is a summation over mu and also a summation over nu. So, let us start with 0, okay, and then let us take, see, omega 0 0 will be 0 because these are antisymmetric. So, there is no such element, but if this is I, where I is 1, 2, 3, this is non-zeros. So, this makes sense. Then you have half omega I 0 j I 0, that is also not going to vanish, plus half omega I j j I j, okay, where I j take values 1 to 3. Now, this one is these two together, you see, because of antisymmetry, this is just double of this. So, half omega, I mean not double of this, is same as this. So, I can combine the two and write omega 0 I j 0 I okay. This is, we have already called define j 0 I to be Ki. So, this becomes Ki omega 0 I Ki plus this one will become, let me write down explicitly, omega 1 2 j 1 2, this you can easily verify. Okay, and I can just write down this as omega 1 2, and our j 1 2 j 2 3 and j 3 1 can be written in terms of j 1 j 2 and j 3. So, this becomes j 2 3 j 1 plus omega 3 1 j 2 plus omega 1 to j3. Okay, so lambda matrix, if I don't show the indices, then it is just, or maybe let me show it, identity minus I. Okay, before I do that, let me do something more. So let me define omega 0 1, omega 0 2, omega 0 3 as beta 1, beta 2 and beta 3. Okay, these are just new names for the parameters I am giving, and also define omega 2 3 as theta 1, omega 3 1 as theta 2, omega 1 2 as theta 3. Okay, just renaming things. Then I get, with these new names, the lambda matrix rho sigma to be identity minus I. Okay, half I have already taken care of in this, beta I k I, this is a summation over I from 1 to 3 minus theta I j I. Okay, again there is a summation from 1 to 3 rho sigma. Okay, so this is the most general form of any Lorentz transformation which belongs to the proper orthochronous part of all Lorentz transformations. Okay, and any other Lorentz transformation can be built by multiplying this with a parity operator or time reversal operator or a product of those. Okay, and these are right now all betas and thetas are infinitesimal parameters. Okay, so you will be able to identify these theta i's with the angle of rotation. You should make sure that you understand, and beta i's with the boost. So these will be related to the velocities. So find out the expressions of beta i's in terms of velocities. Okay, good. Now another exercise, show that if you take a commutator of j I and j j, you get the following. And if you take a commutator of j I and k j, okay, for example j 1 and k 2, etc., you get I epsilon I j k k k. There is summation over k here in both these expressions. So I and j are only the free indices, and then k I with k j is minus I. So that minus sign is very crucial. That is going to be very useful at some point of time for us. Not sure whether I am going to do that in this course, but yeah, these are again the commutation relations. The same commutation relations which we have already written down before, but now in terms of these generators. And I am sure you are already familiar with this one. This one you have seen before in your quantum mechanics course. Okay, and these two ones are new for you, and we will talk more about these commutation relations in another video, but of course these are going to be again very important commutation relations. Okay, so we will stop this video here. Please do all the exercises, and I hope this was not difficult. I have done it in great detail, so should be easy. Okay, so see you in the next video.